Hello, everyone. Sorry for the slight delay. So what I want to talk to you about today is how your systems may fail. So we will not be talking about the happy path. We will not be talking about what goes well with the system, how a well-designed system behaves under great conditions. I want to talk about the things which are not happy. Because what I very often see when I'm looking at designs and people doing some designs on the whiteboard is that they keep going with the happy path. So what happens if this request goes in, this request goes there, it goes like 3 there, and this message goes in, then everything is fine, and then we get a response. But not many people think about failure scenarios. In what kind of normal or bizarre ways your system could actually fail. And what I want to take you today is a journey through different ways in which your system can fail, but also different ways in which you can protect your system. So my name is Tomasz, and I would like to start with this quote, which really resonates with me. Well, you can all read, but I guess you can feel the pain. Many of the systems I see feel somewhat like a house of cards. You take one little piece and everything suddenly falls down. I see someone's taking a picture, so I'll do like a nice pose. Yeah, move on. Thank you. All right, so you probably heard this term 1 in a million. There's even a song about it, which I don't dare singing right now. But 1 in a million in some sense means like it's a thing that will almost never happen. It's like there's a moonshot that's not possible, so let's not even design it in place because there's just no point. But the fact is, if you have a system handling like, I don't know, 1,000 requests per second, it happens every 15 minutes. It's way too often to actually get paged about it. It's a new norm, right? So it's no longer 1 in a million. And even 1 in a billion doesn't happen that less frequently. All right, so let's talk about P99 latency. Everyone talks about P99 latency because P99 is fine and pretty much no one sees it because it's just this one tiny percent, right? Just one tiny percent of the people will actually observe it. Well, as a matter of fact, and I choose Facebook not because it is a very bloated website, but many of them are like this. So when you open up a facebook.com, it makes like 300, maybe 400 these days requests to the server. This is pretty much a guarantee that at least one of these requests will observe P99. So P99 is now your average. It's no longer your outlier, your long tail. So what I want to do throughout the rest of the presentation is go through a set of patterns or a set of failures that can happen within your system and type of patterns that you can apply so that you can sleep safely and you're not woken up at night. So the first pattern I want to show you is the try-catch. I guess you're familiar with it. So essentially, the idea is that when there's an error, just handle the bloody error. And you think that's funny, and I saw at least one person smiling. That's really great. But imagine this situation. So we have this long-running transaction with like 100 of different business steps. And if you dig deeper, you will actually see that there are more and more details, things happening. You can read, so I'm not going to repeat whatever you see here. But imagine at the very end, you get a socket exception on something low level, like no space left on device or whatever. What happens if you forgot about this insane and like amazingly novel pattern of try-catch? Well, all of this gets rolled back, right? So the entire operation will get rolled back because you forgot that some of the operations, like sending an email or creating a report, whatever, could actually fail. We'll deep dive later into how you can tackle with the failures, but just keep that in mind. How often do you actually see try-catches in your code, and how often you just rely on the fact that the exception will bubble up and it will eventually end up with 503. And it's good when it's a transaction because the transaction will roll back, but think about all the other side effects that could have happened in the meantime. Do you actually handle them somehow? We'll get into that later on. Now, another pattern, and as you can see, we're starting really slow here, is a fallback. It's the reason why the presentation is called Better Call Fallback. So whenever you're making a request or creating or running some operation or doing whatever it takes to process your request, think what happens is there any fallback operation? Is there any backup plan you have for this particular operation? So the most common example is that you have some sort of a retail store or a streaming platform or wherever, and you would like to show the recommended products for this given person, or recommended movies, or recommended whatever. And if that service fails, I think you can agree that this is not crucial. So if that service fails, it doesn't mean that your entire business should go down. So what you do You just show like the recommended globally or bestsellers or the most viewed or whatever. In the worst case scenario, you just don't show anything, but you let people do their shopping, right? This is so simple, yet I saw so many services where a very like not critical service was bringing down the entire website. So once again, try catch is your best friend, at least at the very beginning. If there's one thing I would like you to remember from this presentation, but we will see more. All right, so moving on, retries, another extremely interesting and extremely simple pattern. Basically, if you failed, chances are it's going to work the next time because there was a network condition, because there's a DNS failure, very common these days, because you will hit another instance of your service, which actually is behaving correctly. That's a really, really simple way of making your services resilient. And users know that because when a website doesn't work, what is the first thing you do? You hit refresh. So just do the refresh for the user. I mean, not on the front end, but somewhere down the line on the back end. But retries aren't as simple as just try catches or fallbacks, because you do have to think about a few things. First of all, very rarely you do retries immediately. This is, I wouldn't say anti-pattern, but you have to be really careful, because if you're doing retries immediately when an error appeared, there is a big chance that you will just overflow the system, or you will just DDoS the system that's on the other side. You are not giving any breathing room to that system to self-heal. So just let it a few milliseconds, a few seconds, maybe a few hours, depending on your use case, to settle in. And there is a lesser-known HTTP header for that. It's called retry after. It is your responsibility as a client to respect that header. Not a responsibility, but a good behavior, I should say. So that is very straightforward. The server cannot reply to your request, but it tells you explicitly, please try again at 5 o'clock, or please try again in 2 seconds. And just do that, right? Because he knows better. He knows when it's going to be up, and the server knows when the data will be available or when it's going to restart, right? Or some sort of load balancer. Another thing that you should think about when doing retries are exponential backups, and there's always a jitter involved. So exponential backup is pretty simple. When you're retrying, the first retry should be very fast. Probably not immediate, but very fast. Why? Because a lot of errors and a lot of failures within the system are very transient, meaning that they will go away very, very quickly. So, for example, you will just hit another instance from the load balancer, or there was a garbage collection that took 50 milliseconds and you hit a timeout, more on timeouts later, and you just need to retry very quickly. However, if the issue is more persistent, for example, the entire system is down, or there is some network reconfiguration, whatever, you should not spam the underlying service like every 10 milliseconds. Just do it once and then gradually increase the timeout value. So 10 milliseconds, 20, 40, 80, that is the exponential part. However, don't hard code it. And rather than having a hard-coded thresholds of like 80, 160, 320, and so on, add a little bit of randomness. Because that randomness means that not all of your systems, not all of your instances, not all of your requests will try to retry at the same time, which causes another failure down the line. So think about it. Speaking of timeouts, so another really obvious thing, but I was driving a train, or I was a passenger. I was in the train, I should say, one day, and I was running a ping constantly because the network reception was really bad. And what I got was a ping that came back to me after 749,000 milliseconds or something. This is 12 minutes. Right? Does your system actually survive when it gets a response that goes back to you after 12 minutes? Well, essentially, such a system, if you have a dependency which replies after 12 minutes, and typically it's more like 12 milliseconds, most likely you just treat it as being down. But don't wait 12 minutes, for God's sakes, because the entire system will just get stalled for 12 minutes, and you're most likely consuming a lot of resources. All right, let's move on to something more interesting. There's this technique in making ships, and people are making ships for many, many years already, called bulkheading. So bulkheading is this idea that when you have a ship, I think this is called a hull, the thing that you sit on, or the thing that you build the entire ship on. You put like a vertical walls, as if like walls could be horizontal, whatever. You build like walls through the entire hull, so that if there is a hole, if there is a puncture in one of the places of the ship, you don't flood your entire ship with water, just this one compartment. So the idea is, and let me give you a more large scale, like, okay, once I think about it, the Titanic is not the best example here, but you get the idea. So the idea is that there's always just one compartment that's filled with water, but the rest is still dry, meaning that the ship can still operate, unlike this infamous Titanic. So how do we take it to our how do we take this to our engineering practices? If you have a single instance, and it doesn't matter if it's a microservice or a monolith, although it's much harder with the monolith, you probably have some sort of shared resources. You have a shared worker pool or thread pool or a pool of Go workers. You have a shared event loop or whatever. And if there's one flow, if there's one use case, if there's one user who somehow triggered very noisy operation, and by noisy I mean an operation that takes a lot of time, a lot of resources, this will essentially occupy your entire resource pool, so all your threads or your workers. So this is similar to having a ship without bulkheads. Essentially, you take all the space there is, and everything goes down because all the other flows are now suffocating. And when having bulkheads, and you can implement bulkheads using like a bunch of smaller thread pools or a bunch of smaller resource pools, or having microservices, and they are kind of by definition individual processes. This basically means that if one of the workflows is misbehaving, all the others are still working. So think about your service and think about, do you have any place which can consume 100% of the capacity of everyone else and suffocating everyone. Okay, another thing I would like to show you, and as you can see, we're really close to like civil engineering and like people who are actually doing some engineering, not just software. A throttling is this kind of a mechanism that you can also obviously employ in your software. A throttling is this kind of a mechanism in which you are preventing your own application from doing too much. And it doesn't mean you have to have like a hard-coded limit of, well, I don't know, I'm not performing more than one request per second, right? Like I'm not handling more than one request per second. I'm not making more than this many messages sent to the broker and so on and so forth. No, but it just means that you have such a possibility. So if there's an outage at 2 a.m., you can say, my service is not the reason of the outage, but I can put the lever down so that I'm not DDoSing other services. There should always be an option for that. So you can dynamically and at runtime simply say, okay, my service is not gonna produce more events than this amount of time, than this number, because I don't want to put too much pressure on other systems. And remember, this is all like a connected system. So if your piece of the puzzle is misbehaving, everyone else will feel it, especially in a very distributed infrastructure. Okay, moving on with civil engineering. This is a circuit breaker. I guess you know what it is, but essentially if there's too much current flowing through your wires, it just trips off. And then there's no electricity at home, but at least you don't have a fire. Like literally, there's no fire. We can have the same pattern, and it's actually implemented in many systems, and there are many implementations in different languages. We can have the exact same behavior in our system. In our case, it just means that if you keep calling some dependency, so if you keep calling some sort of API or some sort of dependency and it's broken, it keeps sending you 503s, or it keeps timing out, there's probably no point in doing that over and over again for like several seconds in a stretch. There's just no point because it will be down for the imaginable time. So what the circuit breaker does pretty much automatically is that if it sees the error threshold or error rate is too big, it just cuts off the dependency. So from your perspective, you still get errors, but you get them immediately rather than after 1 second, 2 seconds, 10 seconds, whatever is your timeout, because hopefully you do have a timeout. But also, you stop sending traffic to a service which is probably already misbehaving, right? So you let that other dependency or downstream dependency, you let it breathe. Maybe it needs to restart. Maybe it has a hard time with a garbage collection. Just let it breathe for a while, let it restart, and then we can move on. The good news about circuit breakers that we have in our software is that they turn on automatically, right? This is not the case with these physical ones. And the way they turn on automatically is that they periodically, like once a second or once every 100 requests, try to make a single request to that downstream dependency. If it's still down, the circuit breaker remains open, which means it fails instantaneously. If not, if it succeeded, then the circuit breaker closes and you keep operating. So the system is self-healing. And that's a really good theme. Have your systems be self-healing rather than failing and bringing down other services. All right, there are two connected terms. There's thundering herd problem and cache stampede problem. And this can also happen, and it happened to the best of us and to the best companies on the market. So the thundering herd problem is when you have multiple processes or threads or workers, whatever, waking up at the same time to essentially do the same work, or all of them attempting to do the same work. To have a concrete example, I don't know, all your database backups are scheduled at the same time, or some system was down and every other component that relied on that system scheduled that they should start again or they should make requests again in, I don't know, 5 minutes. So everyone wakes up precisely at 2 a.m. and try to make a request to that system, which most likely will go down under increased load. And many systems went down because of this. The solutions for that are actually quite simple, and you can probably already guess. Just smooth out the traffic. So don't let all the requests coming in at the exact same time. Just add a little bit of jitter. So if you have, for example, retries, or if you have some sort of cron jobs, just add a little bit of randomness so that the traffic is smoothed out and you don't need this instantaneous scaling out. A similar problem is cache stampede, and it happens when you have a cached item, and everything is great when your cache is warm. So your data, which is maybe heavy to compute, is cached, everyone else reaches to that cache, everything works great and is very fast. However, when the cache gets cold, or more importantly, when an item expires, at some random moment, right, because you don't really control that, or you don't think about it most of the time, what happens is you will get hundreds or maybe thousands of processes hammering your cache item, and all of them will see that the cache is empty. So for all of them, the cache recomputation will be triggered. In the most cases, it's unnecessary because all of them are recomputing the same thing. But this will most likely bring down the service that was computing the cache, meaning that it will restart and the cycle repeats. Many systems, I think there is an example of Facebook, many systems were brought down for this exact same reason. And there are many ways in which you can, fix that. One of them is, for example, pre-computing the value when you see that it's close to expiration. Or when the item expired, rather than saying that it expired and you need to recompute it, just send stale data while you are doing the recomputation in the background. This is especially important when your recomputation thing is extremely expensive. You don't want to do it more than once. All right, let's move on to the asynchronous world. And in general, this is much less error-prone, or at least superficially, because if you don't wait for a failure, then you won't see the failure, right? That's pretty straightforward. But the other reason for that is that working in an asynchronous fashion allows you to decouple the producer and the subscriber. So it allows you to decouple services temporarily. You no longer have to have two services talking to each other, making request response, because if anything bad happens in between them, then your entire workflow is broken. If there's any sort of asynchronicity, you can break this tie down with all the usual downsides, obviously. So there are many ways in which you can implement like asynchronous processing. The simplest one in process means you can use thread pools or like goroutines, coroutines, async await, whatever. Every sane language has it. But I want to talk about something a little bit more complex, so message queuing. So essentially, and you know very well the pattern, rather than making a synchronous request to another service, just send a message and hope for the best, right? And this is what I mean the happy path, because we just send a message and hope that it's going to be received on the other end. But there are so many questions we have to address. For example, what happens what's the order? Yeah, order, exactly. For example, what is the order? Right? Is the order preserved? If I send two messages one after another, will the subscriber receive them in the exact same order? Or is it random? This is extremely important. Do you want to create an item and then delete it? Or do you want to delete an item that doesn't exist, which is going to cause a failure on the other end, and then create it, having a phantom item on the other end, right? You have to be careful about it. But also retries. So what happens if the producer fails? But more importantly, what happens when the subscriber fails? Someone reads a message and the other end failed to process the message? Will it get retried? Will it rent in DLQ, dead letter queue? Will it get retried on the same instance? Is it possible that I'm processing the message for too long and the same message will be passed to another instance because I'm considered dead because I'm processing for it for too long? There's also this thing called head of line blocking. So if we have perfect ordering, it also means that if you're processing one message, your system cannot process the next one, right? Because we have to provide order. So there are pros and cons, as always. If I want to highlight one thing, it's the at least once strategy. This essentially means you are not, we are very encouraged to retry the publisher. Exactly once is only theoretical, I should say, and at most once strategy, which essentially means we try to publish the message and we do our best. This is something that can work in some cases. I don't know, when you're pushing to front end or when you have a very high volume of updates and you only care about the last one, that's fine. But typically you want at least once, and at least once means essentially if you're not sure if you published a message, just do it again. On the other hand, you have to make sure that the other end is able to deduplicate the duplicated messages, right? Make it easy for them. For example, there is the idempotency key HTTP header. I know I'm talking about HTTP, but you can employ the exact same pattern for messages. What kind of pattern? It's that simple. Every message has a unique ID, and if you retry it, you use the same ID, right? So that the subscribing part can read it, and it can essentially skip the message if it was retried. Talking about message delivery, there's this thing called the outbox pattern. So the outbox pattern, I could probably give a separate talk about it because it's there's a lot of pros and cons of it, but essentially it's the idea that if you want to publish, you want to change the state in your local database, and also you would like to inform other people about that state change, right? This is surprisingly hard. Now, the way you would typically do this is you just like save the state in your database and you send a message. So exactly what I said. But you have no guarantee that the message will actually get sent, right? Because your application could have crashed in between, it could have been interrupted, publishing the message itself could fail because the broker was unavailable, and so on and so forth. So there are a lot of concerns that you have to address if you want to get this atomicity. And the outbox pattern addresses just that. I don't want to like put too much time on it, but just as a kind of a rough algorithm, what you typically do is that you make a change to your local database, and you have one dedicated table which contains intentions that you would like to publish something. It's called the outbox table. So rather than sending the message immediately, you just put that message into a database in the same transaction. Meaning that either your state change to your local database and your outbox table were modified, both or none of them. This is extremely important. And then you have a background process, which is triggered in whatever way. Then you have a background process which just goes through that outbox table and just actually sends the messages with proper error handling and just making sure that it happens at least once. Of course, with all the pros and cons of this solution, like using a database as a queue, basically, in that regard. But this is a really useful pattern if you want to have at least once delivery built on top of your relational database. Okay, let's move on to the next chapter I would like to get you through this journey. So, distributed systems. And I won't dive too much into it, but just a few things which I personally found useful, but also a few things that caught me by surprise when I was doing some distributed work. So there's this thing called leader election. So a leader election is this idea that you have a bunch of nodes which are homogeneous in that sense. They are stateless. All of them are the same. There is a load balancer routing traffic, maybe not even a sticky one, routing traffic to all the instances. But you do need to perform one action at just one node, or you do need one special node, which is kind of a coordinator. So a leader election algorithm is complex on its own, so let's not dive deep into this one. But I wanted to emphasize one more thing. So there's a tendency that if you already elected a leader, so you found this one special node for some duration of time, because that node can go down and then another node should take over. But the thing is that if we already found that leader, it's very tempting to just do the work. right? So all the nodes are doing like normal stuff, and there's this one special node who has one extra job, and that one extra job should not be too expensive. Because suddenly you have a lot of imbalance, and suddenly you have one node or one pod which is doing a lot more work than all the others, right? So it's much better to distribute the work. For example, there's leader who just coordinates who will do the special management tasks. So maybe some round robin, maybe some scatter-gatter or whatever, but don't do everything yourself. What could happen, and I'm not saying it did happen to me, but I say that it could happen, there could be a situation where one of the pods or one of the nodes is so overworked because he's a leader, then that node goes down because it is considered by the cluster as unhealthy because the metrics are so low and so on and so forth. So what happens? Our leader goes down, another node is elected as a leader, another node takes care of this extra expensive work, and what happens next? Yeah, this one also goes down. And the third one, and the fourth one, and the fifth one. So everyone gets this rotten apple, or this hot potato, or whatever, and it just keeps failing one after another. So the lesson here is the leader doesn't mean a system that does all the work. And this can be applied to many other scenarios. All right, this one is a bit exotic, but maybe it will kind of change your perspective, or maybe it will kind of change the way you think about the systems. So let's say, and this goes against like microservices, stateless, cloud, whatever, but this might apply to mobile applications or desktop applications or even a front-end application, which should work in a more offline manner, maybe not with SQLite, but you will get the idea. So don't think about your database as this always existing, always reliable, always available system. Try to think, and this is harder to apply with microservices, but maybe I'll just change your perspective in some other systems. Think about your application as having a local database like SQLite or whatever just on its own disk. And then it can have some sort of replication to more reliable database available globally to everyone. But first, as a first approach, think about just storing data locally and then synchronizing it with like some external storage. And the benefit is actually amazing here. Well, because what you're given is that you have an application that can work offline. And that's pretty much it. We sometimes call it the offline first. So an application, it's typically, I thought it's a mobile phone, yeah. This is kids how the mobile phones looked like, by the way, like 50 years ago. So on your mobile phone, let's pretend it's a mobile phone, you actually have an application that works perfectly fine without the internet connection, on when the internet connection is very spotty and your ping is 12 minutes. And only after you get the actual internet connection, it's going to synchronize itself with whatever, and then you have a sync with all your other devices. So in general, it just works. But if you think about it from this way, rather than just assuming that Firebase is always available or assuming that your RDS instance is always available or whatever, this will make your application much, much more resilient. And if you don't want to go all in, and you still want to believe that your storage is always available, just have this concept of a failure backlog. I'm not sure if I coined it or it's somewhere in the literature, but essentially the idea is that you still store your data somewhere in some external storage and it just works, but have a local queue, maybe even a local persistent queue, which stores all the things that failed so that you can reapply them later. So when the database is back or when the internet connection is back, just reapply all these commands with all the hassles of conflicts and the resolution of that, but I'm not going to get there. But this will actually allow you to just keep working, and you can even fake it that everything is still working, and somewhere in the background, you just reapply all these commands or all these changes. Some architectural styles like CQRS really help a lot with this one. And one last tiny little thing, liveness versus readiness. This is just some random thing that came to my mind. Understand the difference. It's part of like Kubernetes structure, Kubernetes standard, and it should be something that you think about. Being very, very succinct and very, very clear here. So one of them means your application started, and the second one means your application started and is ready to actually serve some traffic. Right? If you have just one probe, if your application is only able to tell, I'm ready, and I can serve the traffic, this might not be sufficient, especially for applications with long startup time, and especially for applications which need a lot of warm-up, like warming caches and so on and so forth. moving on to another part. I lost my mic for a second. Moving on to the next part, so the architecture, and we're going all the up in the ladder. Remember, we started with try-catch, and we're going into much more interesting patterns. So in Terraform, there is this thing called plan. The Terraform plan essentially means that you don't apply your changes immediately. You see what's going to happen when you apply them. And this is bloody important when you're doing changes to the infrastructure. I remember this joke that, what was it? To make error is human, but to make error and automatically deploy to thousands of servers is DevOps. And this is exactly what you want to avoid with Terraform plan. But think about your actual applications. Can you design your workflows, your most critical flows, in such a way that you can run them in a dry run mode? What does it mean, a dry run mode? Well, rather than invoking all the database transactions, changing the database, changing the states, like sending emails, sending reports, generating files, uploading, download, whatever, you just give a plan. You tell the user explicitly, this is what's going to happen when you click that button. And trust me, people really love that feature because sometimes they are scared. They don't know what's going to happen when you click save or publish or save as draft or whatever. But once they see that their manager will actually get notified or not, they are much more confident with the software. And also, it's much easier to test your software. However, this is easier said than done. For example, it requires all your downstream dependencies to also support this mode. So you have to think about it in advance. If you cannot have a dry run mode, try to think about a compensating transaction. So if you have a complex business flow, like repaying a loan or, I don't know, charging a credit card, whatever, can you actually roll it back in a more business or product-oriented manner? So, for example, you send someone a text message saying that their loan was repaid or they have some extra charge on the credit. Can you, in a product-related fashion, roll it back? So sending the reverted message to that person, like, sorry, we were wrong, something happened bad with our system. Or can you reverse the state? That one is actually easier. Or can you create a report that's actually like has all the data but with minuses? Because in accounting, you cannot just change the numbers later on. This is especially important in accounting. And once we're here, if you have a long-standing process, there's this pattern which also like deserves a separate talk, but we don't have time for that. There's this pattern called Saga, and it essentially means that if you have a distributed process that spreads across multiple systems, multiple blocks, and there's like a chain of operations that needs to happen, and all of them is their individual transaction, individual database, and so on. What's going to happen if the chain breaks in the middle? Right? So you have something like, I don't know, reserving a train ticket and then reserving a flight and then a hotel and then a car because you have a system for booking your entire vacation and it broke in the middle. What do you do? Like in the best case scenario, you have a compensating transaction for each of these steps and you just automatically apply the compensating transactions in the reverse order, so that everything gets back to the healthy state. You probably got some side effects, but at least everything is consistent in the end. And talking about side effects, so that's actually something that happened to me like 15 years ago. I don't want to dive into details. I can explain it to you later on. But we once sent 700,000 text messages to a single person. He was not very happy about it, and these were the times where the phone like lost storage very, very quickly after like 100 text messages and so on. So he kept deleting them and we kept sending them, and like 700,000 of them. That's because our system wasn't prepared for that. I mean, it was fully prepared to do that. And like we almost sent 1 million text messages, right? The good news is that we weren't charged for it. But still, that's kind of an issue. And that's because we were not prepared for actually slowing down, or we had no mechanism of discovering that something really, really bad is happening. And that kind of mechanism is called a kill switch. So a kill switch is this simple pattern, which hopefully never kicks in, but you should have it and you should test it. It's a mechanism which, when discovers that something really, really, really bad happened to your application, that it behaves in a way that you have never anticipated, or you did anticipate it because you built it, right? But you get the idea. The kill switch kicks in and it shuts down the operations. For example, there was a company who, after deploying bogus code or bogus configuration change, they pretty much went bankrupt within a couple of minutes. They were losing money like crazy. And that's because, and this is a norm in the financial system, so I'm really surprised it happened. But of course, everyone is smart after reading the postmortem. They didn't have any mechanism of discovering that they suddenly started losing millions of dollars by performing some sort of transactions. They should have had an automated kill switch that would just shut off the system, because it's probably better than just keep losing money through the transactions they make. Talking about shutting down the system, in normal circumstances, you should be able to do a gradual degradation. So what happens if one of the components of your system, one of the microservices, one of the databases, one of the APIs doesn't work? Are you actually prepared for that? Well, that's a tough question. For example, I work at Monday.com. I just checked in the morning, we have like 500 microservices, but only 14, 15 of them are marked as tier 1. And tier 1 means when they are down, the entire system is down. 15 versus 500. It doesn't mean that the remaining 485 are not important, or we can just turn them off and everyone is happy. It just means that we can still operate and we can still run the core functionality, which we have agreed to provide. And this is great. And every time there is an outage and we see that it was a tier 2 service that wasn't supposed to be so critical, but it actually caused an outage, this is a big thing, because now we're trying to figure out why did it influence production in such a way. And this brings us to actually testing the resiliency. So making sure that in an automated fashion, most likely, making sure that your system can still run and it can still perform properly, even under bad conditions. So what I mean by that, so the entire field is called chaos engineering. And this essentially means testing your application against failures of other components. What happens if your database becomes really slow? And typically slowness is actually worse than being down completely. Remember, that was the point of the circuit breaker. I want to fail fast. I still fail, but at least I fail fast, so the customer gets a smarter feedback. So the field is actually pretty big, and there's a lot of infrastructure on top of it. But if you want to start, there are these tools. I think it's the first snippet of code, or one of the first few snippets of code during this presentation. There's this thing called ToxiProxy, and it's just one of the examples. So what it essentially does is you are able to inject some severe network conditions within your testing environment. And you can even run it in your Java or TypeScript or whatever code within your integration test. So we can do it completely in an automated fashion. What happens here is that rather than connecting directly to your, MySQL here? Yeah, rather than connecting directly to MySQL, you connect it to it through a proxy. And then declaratively, you can inject different types of failures. What happens if my MySQL is very slow? What if it drops packets? What if I can't connect to it? How does my system behave under these conditions? Do I behave properly? Do I return the right error messages? Are these 500s or 400s? Or do I return empty response with 200 OK? Test for it. And it's really, really simple. You shouldn't test everything with it, but just your critical flows. Another thing, and I'm just going to go through it very briefly. This is not a talk about observability. Yeah, just have it, but don't have too much of it, right? There's this saying, death by 1,000 dashboards. It essentially means we have so many metrics that, first of all, our Datadog bill is really, really, really high. There are rumors about companies paying tens of millions of dollars annually for Datadog. But more importantly, we don't use these metrics. We don't use these logs in any useful manner because there's just too many of them. So think carefully whether every metric makes sense. And should that metric, when it reaches some threshold, does it wake you up at night? Does it actually show you some sign of something really bad happening? All right, and getting slowly toward the end, let's talk about the culture. I think we've all heard about the so-called postmortems. So when the system goes sour, we write a document and we try to blame which we are trying to figure out how could we improve the next time. But why wait for a failure? We can have a pre-mortem. And essentially the idea of pre-mortem is that we try to visualize what will happen with our system. And we can even test it. We can try to visualize what's going to happen with our system in case of a failure. So we come up with the most common, most probable error scenarios. If your system just uses another API, what happens if that API is down? What happens if that API is down for a lot of time? What happens if you're suddenly flooded with messages? You can perform such an experiment and write a pre-mortem, which is exactly like a post-mortem because it still describes what failed in your application. But it's much better because you're not woken up in the middle of the night. You just do it from 9 to 5, and then you fix the system, and then you can sleep safe. I think that's all from me. A few more links. It stopped changing, whatever. I think that's it from me. So I hope you, if there's one thing I would like you to remember from this talk, is to think about an unhappy paths. For some reason, clicker stopped working for me, but I don't care. So what I would like you to think about is what happens when your system is not performing correctly. What will happen with other components if your component, the one you are responsible for, starts to misbehave, right? Start with a try-catch, test your resiliency, and you will just sleep better. Thank you very much, and we'll see you outside. Thank you.